Dear student, I am Dr. Harel Thomas, Professor in Applied Geology, Department of Applied Geology, Dr. Harisingh Gour Vishwavidyalaya, Sagar. Today, in this course, I will deliver my lecture on Pyroxene-Hornfels Facies Part 2. In this lecture, I will proceed under the following heads: physical condition of metamorphism and summary. Hope it will be useful for you. Try to be regular in course. The beginning of the Pyroxene-Hornfels facies is marked by the instability of muscovite in the presence of quartz. Therefore, potash feldspar plus cordierite and also potash feldspar plus aluminosilicate can coexist in this facies. Further characteristic feature of this facies are the absence of amphiboles, that is hornblende, anthophyllite, gaderite and cummingtonite, and the occurrences of orthopyroxene, that is anisotite and hypersthene. It would be expected that the formation of orthopyroxene on the one hand and the decomposition of orthoamphiboles and hornblende on the other hand would take place of same condition at which the reaction, the lower temperature limits marked by the following reaction: muscovite plus quartz give rise to potash feldspar plus andalusite / sillimanite plus water, and second reaction, muscovite plus biotite plus quartz give rise to cordierite plus potash feldspar plus water at 600 degrees centigrade at 1 kilobar, 680 degrees centigrade 4 kilobar, carried out by Winkler 1976. In calcareous rocks, we can observe the following reaction: gracilorite plus quartz give rise to anorthite plus wollastonite, carried out by Boischer in 1970 at 600 degrees centigrade 2 kilobar. Mg anthophyllite plus phosphorite give rise to anisotite plus water, carried out by Greenwood 1963 at 700 degrees centigrade 1 kilobar. Mg anthophyllite give rise to anisotite plus quartz plus water, carried out by Greenwood 1963 at 745 degrees centigrade 1 kilobar. Scapolite and visuminite also developed in this facies. Anorthite plus calcite give rise to scapolite, carried out by Ellis in 1978 at 750 degrees centigrade 4 kilobar. The upper temperature limit not exceed 800 to 850 degrees centigrade. The following reaction indicates the upper temperature limit: MgCO3 give rise to MgO plus CO2, carried out by Johans and Mitz 1968 at 750 degrees centigrade 1 kilobar. Another reaction, CaMg carbonates give rise to MgO plus CaCO3 plus CO2, carried out by Mitz in 1970 at 850 degrees centigrade 2 kilobar. Thus, there is a fairly large temperature interval within the temperature range of the potash feldspar, cordierite, pyroxene-Hornfels facies, in which orthopyroxene is absent and orthoamphiboles and hornblends are still stable. In other words, there is a temperature interval in which not yet all mineral assemblages discussed in the Pyroxene-Hornfels facies can be formed. Winkler 1967 called the Pyroxene-Hornfels facies as the potash feldspar cordierite Hornfels facies and subdivided it into lower temperature orthoamphiboles subfacies and higher temperature orthopyroxene subfacies. The orthoamphiboles subfacies of the potash feldspar cordierite Hornfels facies differ from the hornblende Hornfels facies in that muscovite in the presence of quartz is no longer stable. The typical feature of the potash feldspar cordierite hornblende Hornfels facies, namely the coexistence of potash feldspar cordierite and of potash feldspar plus aluminosilicate apply to orthopyroxene amphiboles subfacies as well. Furthermore, in general, wollastonite will occur instead of calcite plus quartz. If the temperature is increased beyond the temperature interval of the orthoamphiboles subfacies of the potash feldspar cordierite hornblende facies, orthoamphiboles becomes unstable in the presence of quartz or other minerals. At the stage orthopyroxene formed and orthopyroxene subfacies of the potash feldspar cordierite Hornfels facies is reached. The mineral reaction leading to the formation of orthopyroxene provides data characteristic of the beginning of the subfacies. The following reaction have been studied. Gaderite plus quartz give rise to hypersthene plus cordierite plus water. Gaderite with intermediate Fe-Mg ratio 665 plus minus 10 degree centigrade at P water equal to 500 bars, 705 plus minus 15 degree centigrade at P water equal to 1000 bars, 755 degree centigrade plus minus 15 degree centigrade at P water 2000 bars, carried out by Akela and Winkler 1966. Anthophyllite plus hornblende 1 give rise to orthopyroxene plus anorthite plus hornblende 2 plus water. Equilibrium data for a molecular replacement of 15% of MgO by FeO in the system, 650 degree centigrade plus minus 10 degree centigrade at P water equal to 250 bars, 665 at P water 1000 bars and 665 degree centigrade at P water equal to 1000 bars and 665 plus minus 10 degree centigrade at P water equal to 2000 bars. Chaudhary and Winkler 1967. These temperatures are only slightly higher than those of the previous reaction, temperature range 700 to 800 degree centigrade. Hornblende breaks down at very high temperature 800 degree centigrade, P water equal to 1300 bars, 1000 degree centigrade, P water equal to 6000 bars. Yoder and Telly 1962. Mg anthophyllite plus phosphorite gave rise to inertite plus water. 745 degree centigrade 1 kilobar, carried out by Greenwood 1963. Mg anthophyllite gave rise to inertite plus quartz plus water. 745 degree centigrade 1 kilobar, carried out by Greenwood 1963. These reactions suggest temperature of 700/750 degrees centigrade for the beginning of Pyroxene-Hornfels Facies, the upper temperature limit may not exceed 800 degrees centigrade. The pressure conditions range between few hundred bars to 4 kilobar. The upper pressure limit is suggested by the common pressure of andalusite P triple point of aluminosilicate, absence of kyanite, common presence of cordierite and rarity of aluminium garnet, absence of garnet in peltic hornfels indicate pressure of less than 4 kilobar during Pyroxene-Hornfels Facies. The course content on metamorphic low pressure facies begin with the introduction, followed by the description of Pyroxene-Hornfels facies, the important characteristic minerals in this facies, the chemographic phase relation with the help of ACF, AKF, Al2O3, MgO, SiO2 and CO, MgO, SiO2 diagrams, and mineral assemblages for peltic, basic, calcareous and silica deficient rocks, and finally the physical condition of metamorphism during Pyroxene-Hornfels facies. For further studies, please read the textbooks, references and links given in the text. Thank you very much.